right there. All right, so we are recording, and I am going to get the lecture started. We have about one third of the class here, which is okay. I'm going to get started anyway. So this is our lesson plan for today. I hope you guys had a chance to at least go over the plan a little bit and possibly, a little bit more time, to kind of go over some of the suggested items. You don't have to do everything, okay? Just going through maybe one or two of those items is more than enough. All right, so we're going to get into jump instructions, which gives us a way to alter the path of execution. Okay, and we're going to look into a unconditional jump, which is JMPI, and also a conditional jump, which is JCI. And the first thing we're going to do is to go take a look at the opcode table. So by now, I hope you realize already how important the opcode table is, which means one thing you can possibly do, okay, that's up to you, is to go to File and then make a copy. Then you can comment and add your own description of the instructions any way you want on the same spreadsheet because it's yours. All right, so we'll start with JMPI, which is this instruction. The opcode is there's no XX or YY in the opcode because JMPI does not use any one of the four registers. So it is just 40 in hexadecimal. The mnemonic is JMPI followed with an immediate operand, which means you have to tell it where it is supposed to go or where to continue execution. Now, the third column or column C, which is the RTI, looks kind of awkward, right? Because it says PC gets whatever PC points to, which is exactly what it is going to do. Okay, and when you look at the English instruction, it is simply jump with immediate destination, which means you have to tell it where to go. All right. So given all of this, let's go ahead and check out how it is going to do it. So we'll go ahead and go to our assembler, go to the source tab. So I'm gonna get rid of all this stuff here and then just say a JMPI to a particular location. So you guys can tell me where do you want to continue execution in this case. You can choose anywhere from 0 to 255 because there are 255 locations. 256, sorry, 256 locations. Yes. 222. Okay, sure, we can do that. So now we specify location 222. And location 222, I need to convert it back into hexadecimal because otherwise we cannot tell whether it's going to the right location or not. So let's go ahead and do this in our head. What is 222 in hexadecimal? So you have to do the division by 16 first. 222 divided by 16 is 116, and then a 62. So it's a 1 3, I think. It's a 1 3 on one side, or is it a 1 4 already? You can also do it the opposite way, which is 255 is FF, so you just work it your way backwards. So 255 minus 16 is 200 and what 39, I think, and 239 minus 16 is still more than 222. So I think a D is correct. So it is a 13 times 16 plus something. Okay, so let me track all that calculation. So what do we need to add after this? 13 times 16 is uh 160 plus 48. 160 plus 48 is 208. So 208 plus whatever is 222. Yeah. So that means it is a D E in hexadecimal. Okay. So that's my theory that DE is the hexadecimal representation of 222 without using a calculator, and you guys can kind of independently check whether that is the case, okay? Because you can just do the calculation, which is 213 plus 16 excuse me, 13 times 16 plus 14, is that 222? That's the question. Okay, fine. I'm gonna check it myself. It is? Okay. I was just about to use the command line to check the calculation. All right. So that means we are supposed to go to location DE right after this. Okay. All right, cool. And press the enter key. The assembler is now assembling the instruction. Then we go to the assemble view to take a quick look at what are the bytes that are generated. And we indeed see 40, which is our opcode, and then DE, which is the location that we're supposed to go to. So that's good, right? We double checked everything. Everything makes sense. It takes 2 bytes for these instructions, and the effect is execution will continue at location DE in base 16, or at least that's what we think the program should do. So now we switch back to LogicSim, load the processor. There we go. Go to the RAM component, and then hard code our 40 at location 00. And then the next location is going to get DE, which is specifying where we are going to continue execution at. Are we good so far? Okay. So what I have just done by hand is I just kind of poke the locations in, or poke the values of the locations in, and not using the load ability of the RAM component to load the program in, okay? Because it's a really short program, I don't really need to load the content in. Do we have any questions up to this point? All right. So from here on, I am not going to repeat the fetch process. So I'm just going to quick, fast forward to the decode, because that's when things get, interesting. So I go like 1, 2, 3, 4. There we go. So now we are done with decoding, which means the ROM is pointing, or the microcode pointer is pointing to location 400. 400 corresponds to the opcode of 40. Okay, and then these bits, okay, the 26 bits specified at this location is now controlling the rest of the processor. So now we want to look at all the things that can potentially update and ask how are they going to be updated. Given the RTL, what do you think is going to be updated? Do you guys remember the RTL? Or do you remember what RTL stands for? Check your notes. You should have written it down somewhere. What is RTL? It says here as RTL as well. That is correct. Okay, register transfer language, which means it is describing the operation as as an update of registers. So based on what you see on the screen right now, what register do you think is going to be updated? Nope. We are looking at cell D. Oh, I cannot, somehow the screen does not show what is on the other side. So it is D9, which is this one here. So which register is getting updated according to this? What is on the left-hand side of the assignment operator? PC, that's right. Program counter. Okay, the program counter is supposed to be updated. So now we go back to the processor and ask, is that the case? Aha, yes, it is. Okay, because the program counter has the enable pin connected to PCEN, which is program counter enable, and it is a bright green. So in fact, we are going to update the program counter. So now the question is, what are the usual questions? You know, the register, A register is going to get updated. What is the follow-up question? The, how is it getting the new value, right? How is it getting updated? Which means we're going to track which port. It has got D, Q, EN, and clock. Oh, clock and also reset. Which one do we track if we want to find out who is supplying the value to update the program counter. That is correct. So we look up D, and it is coming out of a multiplexer. So now what do we do? Look at the select. That is correct. It is a bright green, which means it is coming from input 1. We look up input 1. It is coming from another multiplexer. This one also has a select of 1, which means we track this one down for the input 1. And it goes all the way to, guess what? The D port of RAM. Okay, so we know RAM is supplying the content to update the program counter. Um, so what do we check now? Well, the first thing we check is whether RAM is even selected, okay? Because if RAM is not selected, we have a big problem. So is RAM selected? Yes, okay, because RAM cell goes to select and it is in fact selected. But once RAM is selected, what is the next question? Because RAM can do one of two things. Which two things can it do? Reading or writing? Is it reading or writing this time? Are we reading from RAM or are we writing to RAM? So load is a one, which means we are reading from RAM. Okay, so we are reading from RAM, so everything is correct. Okay, because if we are writing to RAM, then the D port would not be driving any information. It won't be providing information. It's going to be an input pin. Okay, but right now it's an output pin. So everything is checking out so far. So what is the next question? Well, but in order to see what is outputting, we need to first answer the question of RAM has multiple locations. Which location is addressed, right? So how do we check which location is addressed? Which port do we check? Nope. Port D is the content at the location, but which port specifies which location we are reading from? Port A, that is correct, because A for address. Okay, very good. So we now track down the A port, and it comes from a multiplexer here. This multiplexer has a select of 1, which means input 1 connects to the output of this multiplexer. So we track down input 1 of the multiplexer, and guess where it came from? The program counter itself. Surprise, right? And that's why the RTL describes this entire operation as PC equals to asterisk or the reference PC, because the program counter is updated by the location in RAM that the program counter is pointing to. Right. So, but why is it pointing to the location that actually has the destination instead of pointing to 40? Because in the fetch operation, there's a post increment PC component to it. So as soon as we fetched the 40 into the instruction register, the next rising edge increments the program counter already, so that the program counter is now pointing to the second byte, or byte 1, I should say, which contains the actual address of where execution should continue. Is that okay so far? All right, cool. So once I have the rising edge, what do you think will happen to the program counter? So let's focus on the program counter this time. So it is a 0, 1 right now, and the clock is low right now, which means the next control T is going to give us a rising edge. Rising edge updates all registers except for the microcode pointer, or I should say it updates every enabled register other than the microcode pointer. So now the question is, how do you think the program counter will be updated when I do a control T? Yes, that is correct. So now we go like control T and voila, it is DE. So the next one is going to reset it's going to reset the microcode pointer back to 000 to start the next fetch operation. So Control T again, and you can see microcode pointer is now pointing back to location 000, which means we are ready to fetch again. But where is it fetching the next opcode from? Which register is responsible to specify where we fetch an opcode from? Nope, the instruction register holds the opcode that we are fetching in. Nope, it's the program counter. And that's why this is also why execution is now continuing at location DE, because the program counter is pointing to location DE. So whatever byte, which is now we know it's a 00, is at location DE, becomes the next instruction that we execute. This is how we alter the path of execution. Are we good doing okay so far with this? Okay. So we can, the actual execution of this program is rather boring, because from here on it's going to go to DE, DF, E0, E1, and then it goes all the way back to location 00, and then we'll go to DE again, and so on. So it's basically not so tight of a loop, but nonetheless a loop. So I can illustrate that by just looking at the content of RAM, because you can see how it is highlighting these locations. And I'm going to go slow so that we can actually see the visual effect of tracking this down. Yep, go ahead. Yeah, this is how we do an infinite loop. Then we will talk about how to get out of an infinite loop. So we'll do a control K, and you can see how this is going to location FF, back to location 00, and then go to location DE again, and so on and so forth. So this is a rather boring program. It doesn't do much, but it illustrates the whole idea of a JMPI instruction, so that we can alter the path of execution. Are we doing okay so far with this? All right, good, good. Okay. So the next instruction is called a JCI instruction. So we'll go ahead and take a look at the RTL of the JCI instruction. It's one member of a family of 5 J conditional branch instructions. So they're all about the same, except for which flag we're looking at. So when you look at it, RTL, this one looks a little bit complicated, because it says PC is going to get the value out of this ternary expression. The ternary expression has a condition of C, which is our carry flag. And if the carry flag is a non-zero, then we dereference the program counter just like a JMPI instruction. Otherwise, we just add one to the program counter to continue execution right after the JCI instruction. Okay, so now the question is, well, that looks kind of magical, because it is conditional. How do we do conditional stuff inside the processor? So that becomes the next question. Okay, and you can see the opcode is a 4-4 in this case. So we're going to change the program to a 4-4, and then we'll repeat this experiment. So we switch back to this thing here, and then go all the way back to location 00. This time I'm going to use the editor to kind of edit the content. Okay, so we go all the way back to here, and this time we specify location 44. Okay, and that's it. Close the window, but then I have to reset the processor without resetting the RAM. The trick to do that is to go all the way to the top. Okay, there is a button, as in an actual quote unquote button on the circuit board, that connects to reset. This is not the same thing as typing Control R as a keyboard shortcut, because Control R would also clear the content of the RAM. This will reset everything except for the RAM. Okay, so it's kind of useful, because I can keep the RAM, but I get to reset everything else, including all the registers. So here's reset. So once again, we are going to get to the decode of this instruction, which is 4-4. So it takes 3 clicks to do it. Control T, Control T, Control T. Okay, 4 clicks to do it. So now we are decoded. Okay, we are now the microcode pointer is now pointing to location 440. So now we want to see what is the magic here. We know the program counter is the one getting updated. The question is, how does it update based on the carry flag, whether it's a zero or not? Okay, so now we go, do the same investigation as last time. Okay, we confirm that the program counter is enabled and it's going to be updated. But this time you can also see how PC Mux is not a bright green. Okay, so one thing about PC Mux is it does not come from the ROM. PC mux comes from somewhere else on the in the processor, but it doesn't come from the ROM, which means something else is determining the value of PC mux. So this time we kind of have to track down how PC mux is getting updated. We have done this before already, okay, at least I think once, but we'll track it down. Okay, so we highlight this one. PC mux is also here, blah blah blah, but it's also here. In other words, PCMux is actually the output of this particular multiplexer. So the next question is, so what controls the which input of this multiplexer connects to the output? So now we have to look at PCMux. PCMux came from the ROM. So this one came from the ROM. We just click on it to find out what the value is. It says 000. So that means input 0 of this multiplexer connects to the output to become PCMux. So now we track down input 0 of this multiplexer, okay, which is this wire over here. It comes from a splitter, okay, a splitter that splits 5 ways. The splitter in return connects to flags, which is the flags register. So that means whatever is in the flags register, bit 0 of the flags register is now connected to PCMux. But because it can either be a 0 or 1, that gives us the capability of making a decision. Because PCMux in return is connected to the multiplexer that connects to the D port of the program counter, which gave us the ability to go like, oh, sometimes we want to use this input, other times we want to use this input. That's how we get the decision making ability out of the circuit. Out of the circuit. Yes. Mm-hmm. Yep. Yep. So what we can do here is we can do a little experiment because the clock has stopped already. So I can actually just poke a value into the flags register and see how it is going to change this multiplexer. In other words, to change the select of this multiplexer here. So you guys can focus on this little wire here when I'm making some changes over here. Do you see how that changed? And change again, and change again. So that means bit 0 of the flags register is really what is specifying PCMux right now at this point. Okay, so now the question is, so what is the difference between input 0 of this multiplexer versus input 1 of this multiplexer? The difference is if you go for input 1 of this multiplexer, eventually it goes to the D port of RAM, which means whatever RAM location that the program counter is pointing to is going to specify how we update the program counter, which makes it exactly the same as a JMPI instruction. We are continuing execution at where we specify the JCI instructions should go. However, if the multiplexer is a dark green, okay, so I can turn it back into a dark green like this, then it is going to use input 0. Input 0 of this multiplexer just comes from an incrementer, okay, or an adder. So basically, we're just adding 1 to the program counter and not performing the jump. So that's how the JCI instruction, is going to determine whether to go to the location that we specify or not, depending on whether the carry flag is a 1 or a 0. Are we good with this? Okay. Now, this entire discussion would be extremely difficult to understand if we do not already understand what the multiplexers are, the layout of the processor, how registers work, okay? Because we have two registers working in tandem. One is the flags register, the other one is the program counter, and also the splitter is also important in this whole thing because we split the output of the flags register into five different inputs into the multiplexer. So PC Mux essentially allows you to choose which input of the multiplexer becomes PC Mux and therefore controlling how the program counter is going to be updated. All right. So are we doing okay so far with this? Okay, great. So now we are done with the JMPI and the JCI instruction. So now I'm going back to the lesson plan. This is one of my most organized days ever, okay, because I actually planned ahead of time what I'm supposed to be talking about. All right, so this is all done, okay? So the C flag is only one of the five flags, okay, that are affected by addition, subtraction, and some of the other, arithmetic operations. And those link back to binary subtraction. Because when we talk about binary subtraction, we talk about the borrow flag. The borrow flag is the carry flag. Okay, I know it sounds really confusing, but most processors do not make a differentiation between carry versus borrow. So if it is immediately after an add, it is carry. If it's immediately after a subtraction or compare, it is a borrow. Okay, we talked about the sign flag, we talked about the overflow flag, we also talked about the L flag. All of those are bits in the flags register. The only difference is which bit position. The only flag that we really have not talked about in binary comparison is the zero flag, the Z flag. So at this time, we are shifting gear to talk about the ALU by itself. So if you go to Logisim, I can now kind of close this one. Okay, let me restart Logisim. You can load the ALU by itself. Okay, even though it is a component of the processor, you can kind of load this one by itself. So we'll go to Documents and then CISP 310. Go to processor and then just load ALU by itself. Okay, so you can play with this. Okay, you don't need to use the processor in order to exercise the ALU. This is the ALU by itself, and you can use it. So it is important to get to know the ALU. So let's just say that we want to perform a subtraction and we want to find out how the five flags are going to be affected as a result of the subtraction. What do you guys want me to subtract? What number to be subtracted from which other number? Hmm? 30 from 58. Okay, so 30 it has one 16. Okay, so there's a 16, and there's a 8, and then there is what was the first number again? 32 from 58. So this is supposed to be the 58. Okay, so I got it wrong. Sorry. All right, so we have one. So 58 has a 32. So 32, this is 1, 2, 4, 8, 16. This is the 32. So once we take up the 32, this is supposed to be 58. So 58 minus 32 is 26. This is 48 now. So we are still missing a 10. So that means we need these two. Yep. So I think that's the one. How do we check? You can actually poke on the wire. So when you poke on the wire, it will give you the binary representation of what is on the wire, as well as a base 10 representation of what is on the wire. You get to choose, by the way, what representation it gives you. You can go to, okay, I cannot remember the menus to get through, but I think you go to simulate, no, window. So you can go to window and then you go to preferences. And once you get to preferences, let me pull the window into a view. Then you can go to, do, 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 nope, I cannot remember now. Template, nope, nope, that's not it. Okay, so it's not preferences. Um, I know there's a way to do it. Options, there we go. Go under project and then options. And of course, it has to open the window on my other screen. There we go. So now we can go to not toolbar, not mouse. Huh. I cannot remember where to change that option. Let me, okay, let's try file preferences. Template, window, layout. That's it, right? It's in layout. Okay, which was displayed earlier. First radix is the base, okay, of the whatever is displayed on the left-hand side of the slash, and then the second radix would be the base of the number on the right-hand side of the slash. So this is how you can control whether to look at things as a binary number or okay, and choose one of the options. You have quite a few options here. You can use binary, which is base 2, which is really useful. Octo, not so useful, okay, but still some people use it in certain occasions. Signed decimal, which can be useful. Unsigned decimal, which can also be useful, and most useful would be hexadecimal. But you get to switch. Logisim does remember this particular setting, which means if you are using Logisim that is already installed on your computer, every time you start Logisim, it will preserve what you have chosen already. So you kind of have to keep that in mind because sometimes the questions in the quizzes will assume that it is by default. Okay, so if you have changed the options already, you may not get the right answer. All right, cool. All right, so we have 58 and you're subtracting what, 32 from 58? So 32 is 1, 2, 4, 8, 16. This is a 32. There we go. So now we have specified the first operand to be 58, the second operand to be 32, and now we want to perform a subtraction. So when you want to perform a subtraction, then you have to look at these operators here and ask which one looks like a subtractor to you. I think it should be fairly obvious. The second one, right? Okay. So now the question is, how do we route this input pin to this particular pin over here? In other words, you look at this thing here, and then you look at this thing here, and you ask what is in between. Oh, it's a demultiplexer. So now you have to ask yourself, how do we configure this particular demultiplexer so that in1 as an input pin connects to the top input pin of the subtractor? Yes. So we need the select to be 0, 0, 1. We upsell to be 0, 0, 1. We also need to enable the demultiplexer because otherwise it's not enabled. So we have to kind of do both of those. So we have to specify a 1 to enable the ALU and then specify 0, 0, 1 for a subtraction. So now we have specified the entire subtraction. So now we can take a look at the output. Okay, so we can track this wire first, okay, the wire that is coming out of the subtractor to see whether it is the correct answer, which should be 28. Because, what? Oh, 26, that is correct. Okay. I was thinking partially in binary. No, partially in base 10 and partially in base 16 and just totally kind of messed up. Okay, so it is 26. Okay, very good. So it is 26. So this multiplexer has the same select and the same enable as the other two demultiplexers. So they're all enabled at the same time and they all switch to the same channel at the same time. Okay, so that means the output of the subtractor is now at the output of the multiplexer, okay? And that's why we see exactly the same thing as the output of the ALU. So do we? Yes, yes. So let's do that, okay? So we have 111, 11, 1010. Okay, so we have 11, 1010, and then the other one is just one followed by okay, got this one wrong. This one is over here. So we have just reversed the two numbers. So now we are looking at 32 minus 58. Okay, so 32 minus 58 is just the same, which is 26, except the sign is flipped. It should be negative 26. So now we look at the output, and it is indeed negative 26 because this one is already set up to interpret the bit pattern as a signed decimal number. So when you interpret 11100110 as a signed 8-bit number, it should be representing negative 26. Okay, as annoying as this may sound, okay, your previous exam has a question that requires you to understand how to interpret bit patterns as a signed integer. So in this case, we have no 1, 1, 2, 1, 4, no 8, no 16, 1, 16. No, this is a yeah, that's a 16. 1 of 32, 1 of 64, and 1 of negative 128. So when you add up all of those, you should get back negative 26. So this is just a reminder of how we interpret bit patterns in a signed integer way. Are we still doing okay so far? Okay, excellent. All right. So now we look at all the flags. Okay, we want to see how the flags are determined. So let me zoom out just a little bit. Okay, so the first one. Okay, so the first thing we want to do is to look at the output of the flag output here, and we look at this bit here. This is bit 0. Bit 0 is coming from this bit over here. This is just a splitter, and this is C out. So now the question is, what is C out? C out is the output of this multiplexer. This particular multiplexer has exactly the same select and the same enable as everybody else. So it is still selecting input 1 to connect to the output. And where do you think this B tunnel is connected to? It's connected to the borrow flag of the subtractor. So that's how after a subtraction, the borrow flag, the overall borrow flag, which in our terminology is T8, okay? This is how it is connected to bit 0 of flags out as a port. Is that okay? So that's one. So now we look at the next flag. The next flag is from bit position 1, which is this one here. It is Z out. Z out is connected to the output of this NOR gate. So this NOR gate is essentially a OR of all the bits as the output, the result of the calculation, except that all the bits are ORed together into one single output, which means, and then negated, which means if you have at least one bit that is a 1 as a result of the calculation, the Z flag is going to be a 0 because it is a negated OR. The only time the Z flag is going to be a 1 is when all bits of the output are zeros. And that's why it's the zero flag. The zero flag is a 1 if and only if the result of a calculation is 0. So it's a convenience feature. We don't really need it because we can use just less than to determine whether something equals to something else, but it is a very inexpensive way to check whether something is a 0 or not. So as a result, we have the Z flag, which is bit 1 of flags out. So now we look at flags out bit 2, which is this one here. This one connects to S out. Okay, so we want to look at what is S out. S out is right here. So the way we compute S out is really easy. It is simply bit 7 of the result of the calculation. In other words, it is the most significant bit or the sign bit of whatever the output is. Is that okay? All right. And by the way, after a subtraction, this is also known as D7 in our terminology because it is bit 7 of the difference. Cool. Now we move on to bit 3 of the flex out, which is this one here. This is overflow, okay? So now we look up, what is O out or overflow out, which is coming from here. We have the same kind of select, okay? So we are looking at this input connected to this output here. And do you recognize this input here? Do you recognize that array of gates? We actually talked about it once. When we talked about the overflow flag in binary comparison, I actually showed this picture once already. Okay, so if you don't have any recollection of that ever happening, I don't know what to do. How about the rest of you? Can you make a suggestion of what to do for people who go like, I have no recollection of seeing this picture ever before? That is correct. First, attend the class. Okay, for people who are not here physically, unless they really watch the video, they're gonna miss it. Two, pay attention, right, in the class. Make sure that you go like, okay, at least every minute, check what is on the projector. Okay. Three, take notes. Okay, because that's how you retain the information. All right. So now, what is this circuit? This is a negation. Okay, when you see a bubble, it means a negation. So we are negating S1 and non-negated S2 and non-negated S out. So now the question is, what is S1 and S2? So we track down S1 and S2 all the way up here. S1 is simply the sign bit of the first input, and S2 is really just the sign bit of the second input, which we know as X7 and Y7. They are the most significant bits or the sign bits of X and Y respectively. So that's basically how the overflow flag is computed. It's the same equation that we have used to compute the overflow flag, except in this case, it is in the form of logic gates. But it's basically the same equation. Yep. Is the Yep, it is the L flag because it is the exclusive OR between the sign flag and the overflow flag. This is an exclusive OR gate. It is exclusive ORing the sign flag and the overflow flag. So this is actually what we know as the L flag in the discussion of binary subtraction. So that's why, when we talked about binary subtraction, I already said that, oh, this is important stuff. We'll talk about this again. And that would be today. So are we doing okay so far with all this? Okay, I hope so. All right. So now what do we do? I have to check my notes. Let's see, where's my. Nope, that's not it. Where's my window? There we go. All right, so we have explored the ALU by itself, how to specify a subtraction and specify the operand as you wish. Okay, so you can specify any two 8-bit patterns and perform a subtraction. This will become useful in the lab. Tag, why didn't you say that first so I would remember to take notes first? Now you say after you already talked about everything that is important. Well, it's not intentional. It just so happens that I forgot to tell people ahead of time that this is actually part of the lab. Um, all right. So next is demonstrate how to capture a trace using just logisim. Okay, this is going to be useful too. All right. So I'm going to write a very short program, assemble it, and then we will kind of trace it. So let's go ahead and I'm going to use my window here to specify the program. I'm going to get out of Logisim right now because I don't need it. Okay, so we'll go ahead and create a small loop program. And it has to start with no op if I want to, kind of trace it in some other way, but we'll just start with the no op. LDI register C with a value of 4, um, and then start a loop here. This is L1 as a label. It marks the beginning of a loop. And then we're gonna do a decrement C, okay, or better yet, okay, I'll do something better. LDI register A with a 1, and we'll do a subtract CA, which means we're subtracting the 1 from register C, whatever register C has at this point, and then we'll do a JZI to L2. Otherwise, we do a JMPI back to L1, and L2 is defined here. We simply have a halt instruction here. All right, so I know we haven't really talked about all of these instructions, but most of it we know already. No op, okay, what does no op do? That's a trick question, by the way. No operation, which means it doesn't do a single thing. Okay, LDIC4 initializes register C with a value of 4. LDIA1 initializes register A with a value of 1. So by the time we get to label L1, we have register C and register A initialized. Subtract CA, okay? That's the only one instruction we haven't really talked about. But what it does should be kind of easy to imply. And if you don't trust your interpretation, you can always go to the opcode table and find out what it does. So all you have to do is to find, subtract SUB, oh, right there, row 22. So this is what it does, okay? It subtracts register Y from register X. Y is the second operand, X is the first operand. So in our program, it is subtracting register A, which is 1, from whatever register C has, okay, which starts with a value of 4. So the first subtraction is going to end up with a 3, then end up with a 2, then ends up with a 1, then it ends up with a 0, okay? And then that 0 is going to cause the Z flag to become a 1, and as a result, it will exit the program because JZI will bring execution to the label L2, which is a halt instruction, when register C gets down to 0. So it's a very tight loop. It just do something a few times. Is that okay so far? All right. So now we look at this program and say, I need to know exactly how many times we are subtracting register A from register C, which means, which is line 5. Okay, how many times are we going through line 5? Yes. If L2 is not defined, the assembler would complain about it. But you can use a label does not have to be predefined by the time you get to the reference of the label. It can be defined after the reference. So unlike C, okay, or C++, which will complain, a label or function is not defined by the time you call, unless you have a prototype, this one does not care. Yes, it will jump back because JZI will not jump for the first, what, 4 iterations. Because remember, register C is initialized to 4, so the first subtraction brings it down to 3, 2, 1, then 0, and then we jump. In other words, the JZI is not going to jump except for the last round in the loop. Now, if the JZI does not branch, then it will just fall through to JMPI, which brings it all the way back to just L1. Okay, so this is the C code. Okay, the equivalent C code is C gets C minus A, which is just decrementing. This is basically saying if Z equals to, okay, if Z go to label L2, and then this one is just go to label L1. That's basically what the C code. Okay, fine. If you guys are, hmm, yeah, yep. Is that good? Well, since I'm here, might as well do this. This is basically the equivalence of the code in in C. This is essentially just the same thing as a return 0. Yeah. but it's not the same, so I'm going to put in quotes. So are we good? Nope. There's no C out. There's no output device. Yep. Question? It's referencing the Z flag, which is bit one of the flags register. Yep. Correct. So the Z flag is affected by the subtraction operation and it remembers it. So by the time we get to the JZI instruction, the Z flag is affected by the previous subtraction instruction. So it reflects whether the result of the subtraction was a zero or not. Okay. Yep. Go ahead. Um, yes. No, it is not infinite. You, if you change which register to what again? It will not be infinite. It would not be infinite. You asked whether it is infinite or not. The answer is not. It is not going to be infinite because it will go around a few times because 3 is uh not okay, the other way around. Because 4 is not divisible by 3, eventually it will go around a few times and it will become 0. Huh? We're subtracting. It will get to 0. Okay, so okay, let's investigate this first. Okay, the question is, if I change line 3 and initialize register A with a 3, the question is, will this loop be infinite or will it get out? That was a question. Mm-hmm. Okay, so just I'll do the calculation down here. Okay, so 4 minus 3 is okay. Let's put comments here. 4 minus 3 is 1, and then 1 minus 3 is FE, I think. Yeah, it is FE. And then FE minus 3 is okay, DCBA. Okay, so it's F. Okay, E is a 15 is a 14 minus 3 is a B. Okay, so that's a FB, I think. But the point is, when if you keep doing this, this one will get down to what? Okay, so FE is a 254. Okay, and now it is 251. So now it will go down to what number before it trips again? Keep. So what? Yeah. Hmm? Well, it doesn't matter whether it's signed or unsigned. The point is, um, okay. So let's take a look. Okay, I'm going to go through the calculation. So the question is, what is n until it becomes, the lowest number that is more than 0. No, it's not 3. Cannot be 3. 2, 5. 255 itself is divisible by 3, so it's going to get down to 2. This one will get down to 2. And as a result, so now the next round is going to start with 255, and then it will get down to 252, and it will get down to 249, blah, blah, blah. And this one will get down to 0. I know it will get down to 0 because 255 itself is a multiple of 2, a multiple of 3. So if you keep subtracting 3 from 255, it will get down to 0. So that means it is not an infinite loop. Now, it doesn't exit when you think it should exit, but nonetheless, it is not an infinite loop. The reason why it is not an infinite loop is because 4 is not divisible by 3. So eventually, it will get down to 0. Is that okay? It does not even matter whether it's signed or not. The subtraction is not is sign agnostic. Yep. The zero flag is also sign agnostic because the sign flag is not used at all to determine whether the z flag should be a 1 or a 0. Well, it is a part of it, but it's not interpreted as the sign flag in that interpretation. All right. So this is actually great. Okay. I like this question because now we can actually say, how does the value of C get changed over time before it exits the loop? Yes. What if A is a 0? Then it would be an infinite loop. Yes. Or if it is a 4, it would also 4 would exit, 2 would exit. Yeah, so it has to be a 0. Then it does not exit. Okay, so let's go ahead and try the program. Okay, so for me, it is a little bit more cumbersome because I'm not using Windows. Okay, so I have to do something like this to put the program into the clipboard. And then we go to the assembler. Okay, and go to the source tab, select the whole column, delete everything in here, and then just paste. So now I just pasted the program. Wait for it to be assembled. So you have to wait until all the messages are gone. Now we go to the RAM file, go to File, and then go to Download, go to CSV, and then specify these programs. This is called Small Loop. There we go. And switch back to um, Logisim, which I don't have running again. Okay, so that's okay. We can just go ahead and run it. Reload the processor file. Oop, not that one. I want the processor, not the ALU. There we go. And then we go to RAM, right click, go to load image, and then specify the file that we downloaded earlier, which is small loop.csv. Now we have the program in. Now remember, what I wanted to do is to keep track of register C, okay, to see how it is being changed over time. So now you have to pay attention because this part you actually have to know how to do in the lab. See, I'm nice, I tell you ahead of time, this is actually useful. So now we go to logging in under simulate, which will give you a window like this. So now you have a selection of what you want to log. So all the things on the left-hand side are things that you can log. Of all of these things, only one thing is really important to me, which is register C in this case. So you can either use register C, which is the actual output pin, or you can go under register bank and find register C over there. It's all the same, okay? It doesn't really matter in this case. So I just pick this register C as an output pin, and then send it to the output. It is in base 2. You go like, oh, but base 2 is really hard to read. Well, change it. Okay, this is now in base 10, base 16, back to base 2. Okay, so let's just go for base 10. Okay, that's a little bit easier to read. Yep. Huh? You go to simulate and then logging. Yep. So now you have a choice again. Okay, I was told by some people, people don't like choices. Don't give them choices. But it is actually my nature to give people choices. Also, for people who don't like choices, I pre-apologize for giving you all kinds of choices. So you now have a choice. You can either use the internal table for logging, or you can use the file for logging. The difference is this one is volatile. which means every time you perform a trace, it is only staying within logic sim. You cannot use a tool like Notepad later on to take a look at the output. So I personally would not recommend using a table. I would recommend using a file. So when you go to file, you get to choose, what file. Okay, so I just like to create a file in the temp folder. So we'll call this small loop dot log. Okay, you can call it anything you want. .txt doesn't really matter. Save. There we go. So now when I run this program, it will log every single change to register C to that file. Okay, so we'll go ahead and take a look at what's going to happen now. Okay, so at this point, you can close this window. As long as you have configured the logger, you don't need to keep this window up, so you can close it. So I'm going to use a control K, and this time I'm going to speed up the processing. So I'm going to increase the tick frequency back to 4.1 kilohertz. Control K until it's done. Now it's all done. How do you know it's done? Because the halt, pin is a 1. So Control K again, and now I can go back to, use. I mean, you guys are going to use Windows, but I'm using something else. But I can still take a look at the log file, which is called small loop dot log, and you can see how it decrements all the way down to 2 this time, and then it goes all the way down to 0 the next time, just as I predicted, because it's all math. It's easy. Is that okay? So let's just say that you have to rerun the program, okay, because that's what you need to do for today's lab. Then the question is, then you have a choice again, okay? Yes, I keep offering people choices when they don't want it. So now you can go to logging, and you have a choice. So the choice is, if you select the same file again, okay, so let's say we want to log to the same file, it will ask you whether you want to overwrite the file or not. Because if unless you do this, if you don't try to re-specify the log file, it will append automatically. Okay? Does everybody understand what I just said? If you do not re-specify what file to use to log the output, it will automatically log the new output to append to the end of the existing file, which is not what you want to do for the lab. So for the lab, you have to remember to re-specify the output file or specify a different output file so that it starts from scratch. Is that okay? So this is an important step. You should specify override instead of append. So now I can rerun the program. Okay, I can go click on that little reset button on the top. Okay, so let me see, where is it? On the left, right? Yep, here. So now I can rerun the program, and it will basically generate a new log to the same file that I was using before. Are we good so far? Okay. So there's one more way to do this. Okay, we got plenty of time today. So if you can get Reefer Spider installed, and some people cannot do it because the Mac version may or may not be working. I don't have a Mac to debug it, so that makes it a little bit difficult. But if you can get it installed, there's another way to do logging, which I have also demonstrated in some previous classes. So you can now go to, let's see, I put it in my documents file, CISP 310 processor, Reefer Spider. And, oh, there we go. So this is a whole lot easier. You just specify where the source file is, which is small loop, oops, dot ttpasm, and it will do everything for you. It will do the assembling, it will run the simulator, it will collect the trace data, blah, blah, blah. And now we can go back to the spreadsheet, which is the assembler. Okay, so go back to the assembler and then go to analysis. So this is the analysis tab. So you can now focus on how register C got changed. So it started off as 01, then it changed to FE, then it changed to FB, blah, blah, blah. Okay, go all the way down to 02 the first round. Okay, whoop, there we go. So it went down to 02. The second time it started from FF, and then it went all the way down to 0, 0. So this is another way to kind of track down, how many times we executed a certain instruction or how a particular register got changed over time. Yep. That is a very good question. It is done by a whole lot of magic. So, you need some pixie dust along with, some shaving of a unicorn's horn and stuff like that in order to get this to work. Um, so the magic of all of this is going into the app script here. So in the app script, there's a do post which accepts the post request that is generated by the River Spider script. So that's the hookup, that's the connection between the two. Nope, this is remote. So you don't need to know all the details, but the setup instruction tells you exactly what you need to do to get this to work. But for today's lab, you don't need River Spider, even though it's a useful tool in general. But in today's lab, you don't have to do it this way. It's just a useful tool to get working. From here on would be good to have it. All right, so that is the next thing that I was intending to cover, which is how to capture a trace using just Logisim. And as time allows, demonstrate how to capture a trace using the assembler's own ability to do the log, which is about Reefer Spider, which I have also just done. Wow, today is not only organized, it is also efficient. But do we have any questions? Any questions? Yes, please. Yes. Yep. So let me show you guys how to do it on the PC, and how to put it onto a quote unquote thumb drive. Okay, so I think we got time to do it. All right, so if you're using a PC or if you're using the PC at the lab, or if you want Reaper Spider to be portable, like, oh, I want to use this PC sometimes, and I'm going to use that PC sometimes, and so on, you can install Reaper Spider on a thumb drive. Okay, it is actually pretty easy to do. So for that particular demonstration, I'm going to use VDI as a virtual machine because this way I don't have to run my own virtual machine. So I'm just going to use the one that the school provides. Okay. So I'll show you guys how to install the whole thing. Okay. It's going to be a lot faster on a virtual machine because it's not on a thumb drive. If you install it on a thumb drive, it can take an hour because thumb drives are actually intrinsically very slow devices. An external hard drive is a much better choice if you can find one. Okay. You can find an external hard drive as in a hard drive, not an solid state drive. It will still be a whole lot faster. Yep. I don't know because they advertise a speed that is in burst mode. This one needs sustain mode because it has to create a bazillion little files, which is really bad for thumb drives that have a benchmark that is based on burst mode. It's not writing to a single file. That's the problem. It's writing to okay, but an ISO is just one file. Yeah. So I think it may or may not work. I cannot tell you for sure. All right. So this is Windows, and I'm going to go back to at least sign in to the drive. Okay. So we'll go ahead and sign in. Uh, uh, mm, don't bother me. Oh, okay. I just missed 1 0. whatever. Back to sign in. Of course, it's going to ask me for authentication. Send me a push. There we go. So for those of you who want to install Reefer Spider on a thumb drive to run in Windows, this is actually a pretty important demonstration. Yep, that's me. I hope. No. Okay. All right. So now I can go to the drive that you guys all have access to. Drive.google.com. And yep, use that account. Mm, mhm. And then we go to CISP 310 in the shared folder under processor. Where is it? Processor. There we go. And under this processor, there's a Reefer Spider or SIG Reefer Spider. That's the one that you need to download in Windows. Okay, it is a pretty big file because it contains, basically an emulator of Linux type, command line. So it's a little bit big. It on this virtual machine is really fast because this thing has a really high speed connection to the Google Drive of the school, so it doesn't take nearly as long as what you might need when you're home. So I would recommend downloading the file at least when you're on campus, and then you install it when you're home. So it's all done. One file in progress. Okay, so it's almost there. Almost. Come on. I'm going to start up a file explorer here. Okay, so file explorer. There we go. Go to downloads. And it's still being downloaded right now. Okay, it's all done. All right. So the extension is a 7Z. So you need to download the tool, your 7-zip, in order to decompress it. Um, so if you have that tool already installed, just right click on the file and then go under 7-zip. And then you can just extract it here, okay? And then you can move the entire folder anytime you want to. So just extract here. This is the slow process. If you are to go through this extraction process on a thumb drive, this can take a long time. On the virtual machine, it is supposed to be a whole lot faster, but we'll see. Yep. Question? Hmm? It is decompressing everything. It's extracting all the files into the local file system. Yep. There's the instruction on the in the link that I provided. I think it will tell it for Macs. It will give you a certain link. I think, unless I right. Yep. It's a much smaller file compared to this one because you don't need SegWin itself. This one includes SegWin, which is a way to run Bash and all the Unix-like tools in a Windows environment. So if you're using a Mac or Linux, you don't need this process. But most people are not using Macs or Linux. So we'll give it a little bit of time. Trust me, this is fast already. This is like supremely fast compared to doing this on a thumb drive. Last year, there was a student who started this process at the beginning of the lab, and we could not finish it by the time the lab finished, which is like 80 minutes. It doesn't take a lot of space. It takes about 1.4 gigs of space on the drive. So it's not about the space. It's about creating tiny little files and a bazillion of them that makes the process so slow. because you're installing essentially a shell of an operating system. Yeah. What? Oh, no, no, no. This. There's nothing recursive about this. Well, we'll just let it brew a little bit here. But this tool is really useful. Okay, so let me go back to the topic here. So what we are talking about is going to this link here. So let me follow the link so that I can show you which part to read. Um, Go to the share file folder and download the zip file for Mac OS or the 7-zip file for Windows. I did not even bother to talk about how to do it in Linux because nobody uses Linux. Does anyone use Linux? Oh, okay. So the zip file should work with Linux too. Because I think I made the commands exactly the same regardless of the operating system. Mac OS is interesting. The earlier version of Mac OS has a slightly different way of treating text files, but the current version, the most up-to-date version of Mac OS, actually has a Linux or compatible way of looking at text files, which is Unix also compatible. So I think they changed the standard somewhere so that the script also has to be changed a little bit to make that work. All right, so let's check it. Okay, this may not complete. Okay, we still got 5 more minutes. We'll give it a little bit more time. Oh, look, it just jumped. But I do want to show you guys how to get this done because it's once you get this done once, you can run Reaper Spider. It really makes the whole process faster. So while this is running, I am going to, right. So uh, the other thing you also need to do is to make a specific copy of um, the assembler. So this is also important. So let me show you what else you need to do. So you have to go to assembler student. Okay, do not make a copy of the usual assembler. Make a copy of this one. Okay, this is the one that you need to make a copy of. So right click and then go to make a copy somewhere. Make a copy. There we go. So in my case, it's making a copy in the same folder. In your case, you probably want to open it and then make a copy inside the file menu so that you can create it in your own folder. So now once we have this, you can open it. And the step that you need to do is to go to extensions, go to app script. I mean, the instructions are already documented, but this is uh, go to deploy, go to new deployment, and then go to web app, and I believe execute as me and anyone can have access. So click deploy, and after this step, okay, this is the important part. Authorized access, okay, fine, blah 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 blah. I already have all your data. Okay, so this is the important part. Okay, you have to remember the URL to this particular URL. So copy that. Okay. Hmm? No, this is the URL specific to this particular copy of the assembler. So after this, you can now switch back. Oh, okay, I switched in the wrong operating system. So now oh, this is done, almost done. Woohoo! All right. So now you go to the folder. Okay, you have to get to the folder. Click on SIGWin. Click on SIGWin. Click on this one, SIGWin Portable. So what it's going to do is it's going to start a new command line interface that looks more of a shell from a Linux system. So this will take a little bit of time. Da-da, da-da, da-da. Okay, just we're almost there. Almost. I know you guys are ready to go do the lab, but this is important. All right, there we go. Okay. So now you can do ls to show the folders, cd to river spider, do another ls. So this is the important part. Okay, do a cat greater than webapp.url and then do a paste. So I think Control V would work. Yep, it does work here. Okay. No, no, that's not the right. Okay, let's do it one more time. And how do we click? I think it's right click, edit, paste. Nope. Okay, so I did not select correctly earlier because I was using the wrong operating system, I think. So let me check. There we go. Copy. Okay, that's definitely the wrong operating system. So get back here and we want to edit, paste. Nope, that's still the wrong one. Right click. Nope, still clicking the. I don't understand why it is not getting the right content. Let me do it one more time. Hmm? It's Windows, that's right. Windows does not like Linux users. Okay, so it is supposed to be copied. Okay, and I need to paste over here. One more time. Okay, paste. Huh? Well, it should be using the clipboard in the virtual operating system, not from the host. But it is pasting from the host instead of from the other one. Exactly. Yep. I know. So it's not copying from the right one. Oh, there we go. Control V this time works. Okay. Then what? Oh, I forgot to run the command first. Okay, there we go. One more time. Woohoo! Yes. Control D after this, and now it should work. So I can do a dot click submit. There's a test program included already, so it's test.ttp.asm. So we'll see. If it doesn't work, it would have complained already because it would not be able to make a connection to the server. So now it says, assembler finished, validating object code. Object code is good, starting simulator. Logisim is pre-installed in River Spider, so you don't have to reinstall Logisim. It's all done. Trace is already uploaded. And now, okay, we'll double check in the browser to make sure that the trace is all good. So now we go back to the assembler, which is this one, go to the analysis tab, and everything is good. Okay, so that's how we use River Spider on the PC. So at this point, okay, I need to kind of finish this also. So at this point, you can close this window. When you're done with River Spider, you can type Control D to close this window, or you can just click the usual X button. So right now, you can move this entire folder, Sig River Spider, from the hard drive onto a thumb drive. Okay, it's going to take a while, okay, but it's a simple process. Drag, drop, go to sleep. Then when you wake up, everything will be done. Hmm? Unless there's a problem, yes, but I don't expect any problem. So the idea is do this on a hard drive, do not do it on a thumb drive. Okay. So now all is that is left is to give you the access code for today's lab. So today's lab is called, where is it? Down here. Simple branching and code analysis. Okay, so now we make it visible. And obviously every time something is called introduction to, fundamentals, or foundation of, it is never easy, right? Yes. So the access code is what again? Joy, that's it. Yep. Joy is trademarked, by the way, so it's pledge.